Alrighty. Good afternoon, everyone. So today we're going to do section 9.2. We're also getting a 10.1. Just 10.1 is an introduction to the hypothesis testing. And so we'll be able to cover 9.2 and 10.1. We're taking off where we left before in 9.1. It's still confidence intervals. 9.1 was confidence interval about a population proportion. So we're going to find the confidence interval about a population mean. So it's going to be very similar, except for our point estimate, that thing at the beginning before the plus minus, we won't use p hat, we're going to use x bar. Okay? So I'm going to write a formula on the board. I'll write it out, and I'm going to cross things out and show you what the real formula is. I'll explain it. So I'm going to be like, all right, a confidence interval. I'll put my, I'm going to put the point estimate here. This is the math formula for it. The point estimate. I'll put a plus, minus, and then I'm going to put the margin of error. All right, margin of error. And this formula's on that sheet that I just passed off to you, but I want you to see this. So the point estimate, we're definitely going to use the sample mean as our point. Boy, if we're trying to estimate a population mean, we're going to use the sample mean as our point. Go out and get a sample mean, right? Sample about 30 cars or 30 people and get an average. Plus minus, now do you remember this? I had to put like a z-score, and this meant how many, like z-score will tell you how many standard deviations above or below the mean you have. So z times the, this is going to be the number of standard deviations right here. So I'll put SD for standard deviations. So how many standard deviations? And we're talking about the distribution of the sample mean. Okay. So then, what's the formula for the standard deviation of a sample mean? This is coming from section 8.1. This had an S here, and this had the square root of n. Okay. So here it is, but this is not the exact formula that you're going to use. We'll talk about that. I'll explain why. So this should be it. You're like, there's our confidence interval. We got the point estimate, plus minus, z-score times s over the square root of n. The story goes, there's a gentleman, his name is William Gossett, and this is like 100 years ago. And he worked for Guinness Brewery. Everybody familiar with Guinness Brewery?
The beer?
Guinness Brewery, yep. Still exists, right? Well, his job was making sure that beer tasted, you know, just perfect. You know, the stout of the beer and everything. That was really his job. And he did a good job of it. But he actually was really into mathematics, statistics, especially statistics. And he ran numbers and everyone, and he ran into trouble with something. He knew there was a problem. See, he had to deal with small samples. Now, everyone, he was tasting the beer, right? Trying things, mixing, tasting the beer. Does anybody understand why he had to use small samples?
Because
It's not like he had a team of people, me, what was going on?
Your taste goes away the more you drink.
Or something, well, something else. He didn't have like 100 people to taste his beer for him. Who's tasting it?
Oh, just one person.
Yeah, William. So what would happen if he used a large sample size? He'd drink beer all day.
He'll get drunk.
All day long, he'd go what?
Drunk.
Stumbling home and stuff, right?
I want that.
So he had to use these small, you know, little sips, small sample sizes. But he knew something was going on, something was wrong with this. He knew there was a problem. And he found out when the problem was this, that this right here, he was using, or excuse me, let me put this here. This was here originally. So I apologize. And when this is what we had from section 8.1. So right here I'm going to put, this was section 8.1. This was the standard deviation for a sample mean. What he was doing, everyone, he was using S in place of this. And that was causing trouble for small sample sizes. So, all right, let me get out the yellow chalk. So he replaced this with a what? With an S. All right, great. But then he had trouble, so I'm going to put the sad face. He realized he had a problem, right? Because of small sample sizes, this really wasn't working too well. So he created what's called the t-distribution. So when, because of this, don't worry, he fixed it. He came up with it. He said, we're not going to use z, we're going to use what's called a t-distribution. So let me rewrite this. I'll put it up there and I'll leave it all class. This is actually what we're going to use when we're trying to estimate a population mean, or do any inferential stats about a population mean. Okay, so let me write this out real quick. And I saw some people had some hands up, that's good, you had questions, but I'm going to put up real quick. Confidence interval equals an x bar plus or minus, not a z-score, but a t-score. I'll talk about that, the t-distribution. I gave everyone copies. And then you're gonna multiply the S over the square root of it. So, oh, what were the questions?
S is for the sample and that thing is for the population, right?
Exactly.
See-
So does this make sense to you, Art? Gossett didn't know this.
Uh-huh.
If we're trying to estimate a population mean, we don't know the population standard deviation. Does everyone agree?
Yes.
We don't know that. So he was using a sample standard deviation in place of that. And there's the trouble. Now, it works fine. I'll tell you what, it works fine if you got large sample sizes. Because of law of large numbers. It works fine, everyone. But you get a little trouble, you get a little bias, you get variability when you got really small samples. Well, no problem. He fixed it with this t-distribution. Cool? So anyways, everyone, I do want to highlight one important thing. Would you put this in your notes? Ready? The question is, what is the key criterion why we use a t-distribution rather than a z-distribution when doing inferential stats about population means? And we're going to come up with the answer. And then we'll finish this up. All right, what is the key criterion? Yeah, criterion, and you can just go reason. What's the key reason? What's the most important reason? What's the paramount reason? What is the key criterion for using this letter T, which I have up here right now, rather than, what have we always used?
Z.
Z. And you go, when are we going to be doing this? When we do inferential stats. Inferential statistics. You can just put STATS, period. About inferential statistics. And this is dealing with the population mean. For population means. Okay, someone puts this out, I'll put a question mark, we're going to put the answer. What is the key criteria, the key reason that we're using this T rather than a Z? When we're doing inferential stats, that means doing confidence intervals, but we're going to do more inferential stats. We're making inferences on populations. Inferential statistics for population means, or about population means. And the reason was right there. So let me circle it. What didn't we know? This is called the trouble. This is the reason. This was unknown. That's what caused this whole dilemma. That was the start of the entire trouble for Gossett. He discovered it. Hey, by the way, you know what happened in real life? He wanted to publish this. Well, this is a business, everyone. And you don't a lot of business like to keep secrets? Because of competition and stuff? So the Guinness Brewery had a policy. You can't publish anything, you know, that's coming out of this company. He was like, listen, this is not going to make our competitors any better. I want the entire world to know about this. So they're like, okay, listen, we don't want any of our other employees to get upset. Publish it, but publish it under some other name. So not your name, William Gossett. So he published it as under the name student. So it's called the student's t-distribution. That's a true story. So that's what it's called. If you Google this, it's called the student's t-distribution. They wouldn't let him publish it just because of that reason. All right, so we got our happy face. This is going to work, but I'm going to put the answer right here. What's that symbol right there called? This thing.
Standard deviation.
Yeah.
Not sigma, the other one.
And I'll erase all this. This thing, everyone, is called the population. Oh yeah, it is sigma.
Sigma.
But it's the population standard deviation. And the trouble was, you go, what was the key reason? This was unknown. That's the reason. I think it's so important you know that. So that's why I'm going to put it here. Make sure you remember that. It's the main reason why we use T rather than Z. It's what caused the entire dilemma. When we had this, let me write it up again. Remember I had this first? And I had this? Well, what was Gossett using in place of this?
Yes.
He was using, because we didn't know this, look, it was unknown, he used this, it caused trouble, so then we had to replace this with a what?
T.
But what started it? That thing. You go, what is it? The population standard deviation, it's unknown. Now, hey, on a test, if you blank out, would you look at that sheet I just handed out? Somewhere on that sheet it shows that. It goes, this is unknown, this is the reason, this is unknown. Cool. Hey, by the way, I'll remind you of this in future classes. I think it's great you know this. Hey, to keep things simple, everyone, last class, 9.1, we did confidence interval about a population proportion. We use Z, right? Now we're doing confidence interval about a population mean. We're not going to use Z, we're going to use what?
T.
T. So to keep things simple, we're just going to say, whenever I'm doing inferential stats about means, we're going to use T. Now, what's a good way to remember this? I got a way that works for me. I don't know if it's going to work for you. Does anybody know Mr. T? He was in the Rocky 3 movie. All right, he's really mean looking. Has anyone seen him?
Yeah, 18.
Tough. I mean, if you see Rocky, I mean, tough guy. So I always think mean Mr. T. I hope that helps. Mean Mr. T. So whenever you're doing inferential stats about what? Populations means, you're going to not, don't use Z, use what? Use T. And you go, why? There's the reason. There's the reason. Cool? By the way, I do want to point out, we'll talk about that T distribution. It's not a big deal if this is a large sample size. So if you got like, if you sample like 150 people, I'll be honest, it doesn't make a huge difference at all if you use Z rather than T. This was really a problem because Gossett was using small sample sizes. So, can we talk about the T distribution real quick?
Yeah.
Then we'll get to a problem. And we're going to copy this. I think one needs it in that one row right here. Would you pass it back? There you go. All right, this is the T distribution. The T distribution is like the Z distribution. The T distribution is bell-shaped. Here. Whoop. It's bell-shaped. But it's based off the sample size. Okay? Gossett invented this so that it changes. This changes depending on the sample size. Now, does anybody remember my story about degrees of freedom about 2 months ago? I said if you got 6 donuts or you got 5 degrees of freedom, you know, because the 6th person walked in the door, there was only one donut, and they had no freedom to choose. Do you remember this story? So 6 donuts, 5 degrees of freedom. Well, the formula, because on this sheet you're going to see a DF for degrees of freedom. I'll put this up here. I'll leave it up all class. Degrees of freedom always equals sample size minus 1. DF for degrees of freedom. So just to make sure everyone understands degrees of freedom, it accounts for bias. If you got a sample size of 4, DF is 3. If you got a sample size of 10, DF is 9, right? If you got a sample size of 100, what's DF? 99. Anyone got that? Yeah. Because on this sheet, look in that left column, at the top left, does everyone see a DF? So when you look at the number that you want for your T-score, we're all going to look, well, what's the sample size? And then we're going to look at the degrees of freedom. Okay? Cool. And by the way, it doesn't have every number, so we use the closest number we can from the table. It's going to be totally fine. Does that sound cool? And so this changes depending on the sample size. It's bell-shaped. In the middle, guess what T equals?
0.
Just like Z, T equals 0 in the middle. T equals like a 1 here, and a 2 here, and a 3 here, and a -1, and a 2, you bet. But most importantly, I want you to know that this thing, in this table, the bell actually kind of changes. You know, the shape. It stays bell-shaped, but it keeps changing depending on the what. So I'm going to draw a few bells here. It changes depending on the sample size. And this is my favorite part. As n approaches infinity, the T distribution turns into the Z distribution. Isn't that cool? So look at the very last row of this sheet. Look at the very last row of this sheet, above those percentages. Look at these DFs. It went 80, then it went 100, and then it went 1,000. So does everyone see this? Degrees of freedom, this is the T distribution. 80, then 100, then 1,000. What's the next letter? Z. So what's happening after a sample size of 1,000? You might as well use which distribution? Z distribution. So that's what's key to this whole T distribution. Eventually, you get a sample size big enough, like 1,000, it's turning into the what? The Z distribution, as n approached infinity. Gossett made this to account for very small what? sample size to count for the bias because we didn't know that daggone population
So,
segregation.
T distribution the same as Z distribution, just for small size.
Yep, it's not the same as it's the same as when
It becomes
n becomes humongous.
humongous.
But this had to be invented to account for this variability over here, just with means. We don't need this for the population proportions when we're trying to estimate a population proportion. He just knew when this was like a sample size of 10 and a sample size of 30, dealing with putting this in place of this didn't work right.
So like Z equals to like X minus whatever mean divided by standard deviation. What is the formula for T?
Yeah, I love it. Everyone, remember how you did this? Find your z-score, and we went like this, and you went like this, and you went like this. So now you're like, yep, I can do that with t now. You're like, I'll just take t and I'll do that. The only thing is, we won't have to do that today, because we got this ready to roll right here, right?
Okay.
But you're going to do this just like this when we get into chapter 10.
Okay.
Cool? And the only thing is right there is, remember how to use the section 8.1 formula?
Uh-huh.
That's what we use, but we will do this. You go, oh, I'll be in, this will be in section like 10.3. You're gonna be like this. Oh, in place of this, I'm gonna use this. You're gonna go like that, you're gonna put your X bar here, and you're gonna put that mean there, just like that.
Huh.
Isn't that cool? Let me put a bar over that. But I do wanna point out, everyone, what I wrote on the board now, you don't have to copy. That won't be necessary till section 10.3. But that's how you get the t-score. And you're like, thanks, Gossett. Which she named the student's t-distribution. Hey, thanks for listening to my boring story. I just think history, I think it's good to know where this stuff comes from, right? So when people go, you know, there's probably stat teachers who don't know where T came. Why do you just use T? They don't know the real reason. You know the real reason as a student, which is cool. All right. So I got this up here. We've got the T distribution. Everyone gets a copy. That gets attached to the test, right? That gets attached to the final. So you have no trouble having to figure out a t-score, and we'll do it in the problem. But we're only going to use this t table when we're doing inferential stats about what? What word? Mean, because mean Mr. T. Are you ready to do a problem?
Yeah.
All right, this can be started. I'm doing A and a B and a C and a D and E just like last class with their proportions. I looked through this morning, Evan. I like on page 449, number 34. So I'm going to write that down, everyone. This is in section 9.2. It's on page 449. We are going to do a complex interval problem. I'll read it to you. This is in section 9.2. Okay? We're going to do number 34. All right. Now, Caitlin, I do want to point out the author said, just do this. We're going to make it like A, B, C, D, E out of this problem, so it's really clear. So I'm going to read some information to you. And we're eventually trying to estimate a what? A population mean? As we get numbers, can we write the numbers down off on the left side? Does that sound good? I think it's good. It's a good practice. You read a word problem, every time you see a number, you write it down and it's simple. All right, here we go. Tensile strength is the amount of stress a material can withstand before it breaks. Researchers wanted to determine the strength of a resin cement used in bounding crowns to teeth. Now, is anybody going in that field? I know in dental hygienists, anybody going to do something like that? I'm just curious. Ooh, we already got one hand. But hey, they're talking about those crowns. Those crowns that the dentist puts in. So anyways, they're actually talking about the strength of that resin cement. I mean, crowns will sit for years and years in people's teeth. Sometimes they replace and put another one, but they can what? That cement, it can get, yeah, it can fall out and stuff. So they're trying to test the strength. So the researchers bounded crowns to 72 extracted teeth. Okay, there's our first number. 72. All right, I write it. What is that? What's symbol? What do y'all think? This whole problem is not about people, it's about their teeth.
Sample.
That's the sample size. And so we're going to give that a lowercase n. Does that sound good? Mm-hmm. Yeah, they're talking about teeth. We're like 72 teeth. So n equals 72 in this problem. It's the sample size. Hey, because we're dealing with t, I might as well write it right below it. Who can calculate df, degrees of freedom? I bet you can do it. 71, right? Might as well write it down, right? I know it wasn't in the problem, but we know degrees of freedom is always sample size about 71. Cool. All right, so there's 71 degrees of freedom. Let me keep going. Using the resistance test, they found the mean strength of the resin cement to be 242.2 newtons. All right, so let me write that number down, 242.2 newtons.
You just put big N for newtons.
And they said the mean. Well, when this isn't mu, this is that's the x bar. That was the mean of these what? 72 teeth. That was the strength. Newtons, everyone, they use newtons for force.
It will be 242.2.
Oh, thank you.
When I wrote 24.2.
242.2. All right, let me keep reading. Standard deviation was 70.6 newtons. So, all right, 70.6 newtons. Some of you don't even have to put the big N if you don't want to. I know it's not a physics class, but that's the force. 70.6 newtons force. They said standard deviation. Well, that's not this symbol because we don't know that. See, this is what? Unknown. So I'm going to use sample standard deviation symbol, which is,
T.
it's just a little s, right? If you don't know the symbol, just you can write it down. You go, that's the sample standard deviation. All these numbers were given. All right. Now, eventually, everyone, they're going to tell you what kind of confidence level to do for this problem. 95% confidence, 90% confidence, 99% confidence. They're going to give you something. Here it comes up right now. Based on this information, construct a 90% confidence interval for the mean strength of the resin cement. So you and I are going to perform and construct a confidence interval, but it's going to be a 90% confidence interval. I'm going to write that down before I forget, right? Cool? All right. Everyone, that number they gave right there is going to help us figure out T. But that's not T. We're going to have to read it from the what? Table. There should be enough information. I want to see these numbers. It's not a crazy puzzle to us. With all these numbers given here, you and I will eventually pull out this sheet, and we're going to figure out the t-score to put right there, and I think you'll find it fairly easy. All right? But I'm going to get this started. Here's my first question, letter A. You know I did this last class. Can we verify the requirements for this problem? And what do I mean? I mean, first of all, I want to make sure it was a random sample. And I'll be honest, when I was reading those words, I didn't hear the word random, did you?
No.
Now, sometimes it's really hard to get things done randomly. I didn't hear anything, I didn't read anything about this sample being random. So everyone, don't you agree that's the first thing we should look at? Maybe there could be, what if this was all done in one dental office? That's a huge bias, do you agree? Mm-hmm. I didn't see anything about this, but everyone, perhaps they just didn't include it in the wording. Maybe I should contact the author, ask about this, but how about we just assume it was a random sample? Does that sound good? Because if not, don't we already have bias?
Yep.
Huge bias. So well, we're going to assume it's a random sample. Randomization is the best defense against bias. Remember that in this course. Randomization. Best defense against any type of bias. I didn't see that word. All right. That's first I'm looking at as a mathematician, statistician. Second of all, do you know what the check is for means? The sample size, because we have no knowledge about the population, has to be greater or equal to 30. Do you remember this? Mm-hmm. And everyone, did you get a copy? Everyone got a copy of the sheet, right? You know what that memorized? It's on here. It is on here. But the sample size, it's conservative. We just want to make sure it's greater or equal to 30. Is it?
Yep.
So I'm going to put a comma. I'm going to write that. We're good to go. Sample size greater or equal to 30. I assume that this sample is a random sample. We're good to go now, right? Have you noticed there's two checks? One of them is the n times the p times the 1 minus p is greater than or equal to 10. That's for proportions. What is it for means? N has to be greater than or equal to 30. And you can always look it up on the sheet. All right, so let's get the letter B. And when you need to now construct a 90% confidence interval. Okay. Here we go. Construct a 90% confidence interval. I'm going to set it up. Everyone, I'm going to write CI for confidence interval, equal sign. Oh, I don't have this memorized. You can look right off this sheet because it's on there. It's right there. And when I do want to point out on this sheet, I do have another one listed. Anyone have a copy of this? Can I tell you which one we don't need? The one that's all the way up in the top left. Would you just cross that out with a pencil right now? See the X bar equals and there's a Z there? That's this population standard deviation is known. You see that, Art? Mm-hmm. I want to see that in the top left. Okay, let's see that top left one where it says that. But see, population standard deviation is known. You know, that's not what happens in the real world, right? So put a line to it. Which one are we always gonna use?
Unknown.
Smack dab right in the middle. So do you see it? Look in this top row of this sheet, right here. That top left equation there, Mia, cross it out. We're saying we're never gonna use that. We're always gonna use this one, which is in the smack dab middle. You see it in the middle of the sheet?
So the first
Yeah, crossed out the top left one, and then the one in the middle is the one we're gonna use. Sound good? Yeah. All right, here I go. X bar plus or minus, not Z, but T, S over the square root of n. All right, let's start filling things in. What's that number?
2.2.2.
Come on. You're good. Just fill in the numbers. We'll come back to the T, everyone. I'll put it in yellow, I'll highlight it. We'll do that last. What's the S?
70.6,
70.6, square root of, what's the sample size?
72.
And when we are almost done with this confidence interval, we'll crank it out on a calculator. We have one little thing to find.
T.
You and I have to find this what?
T.
T. So get your T tables out, or your T distribution out. You go. This gets attached to the test, right, Mia? Yep. Final exam too? Oh yeah. It's always available. First thing is, we gotta look in the left column at DF. DF stands for degrees of freedom. What DF are we looking for?
71.
71. Now, and if there's no 71, I want you to find the closest number to 71.
80.
Yeah, there's a 60 and 80. Does everyone agree 80?
Yeah.
Yep. So we're going to take the closest. If it was smack dab in the middle, it doesn't matter which way you go, but 71 is definitely closer to 80. Let's use 80. Now, we're going to move off to the right. What was the confidence interval?
90.
Everyone, look at the bottom of the sheet. Do you see all the percentages?
4.66.
See, everyone see the percentages way at the bottom?
Mhm.
Denora, do you see those? Oh, cool. I need you to line up. You know how to read tables. Line it up. Be like, all right, what's the 90% associated with we're using the 80, right? So when we're using this table, we're going to use the 80 for the DF. We're going to line it up with what's 90% confidence there. We're going to line it up. And what do you get?
1.664.
I heard it.
1.664.
1.664. Isn't that cool? By the way, if you look at the top column, what's the decimal associated with that? I want to show you what's going on here. 90% from the middle meant how much is in each tail.
5.
So there was 5% here in that tail, but what are these two t-scores? This t is 1.664, and what's this t-score? Cool.
So we don't do any more the inverse norm?
That's right. Isn't that cool? But I'm sure there's some students curious right now. And isn't it easy to find this from a sheet? Yeah, no one's gonna have trouble doing a sheet. Now, I do get people who go, yeah, but come on, this is the year 2016. We've got technology. Can I do this with a calculator? Well, who's got a TI-83? All right, TI-83 people, you need this sheet.
Oh.
You don't have an inverse T button. Who has a newer like TI-84 model? All the new models have an inverse T button. So if anybody didn't feel like looking at the sheet and wanted to get this off their calculator, they'd have to inverse T, and when this is what you do, this would give you the t-score. So when t-score would equal inverse T, you'd have to put in, what's in that left tail?
0.05.
0.05, but then you have to put a comma and you gotta list the degrees of freedom. So how many degrees of freedom did this have? You just go like that. Now I'll be honest, everyone. You know I have a graphing calculator. My graphing calculator doesn't have the inverse T on it. Isn't that funny? You know, I can go to the math department and complain. Hey, where's mine? No, I'm fine. I'm fine. Just I used a T table, right?
Where's the inverse T?
You might not have it. Did you go to distribution?
Oh, no,
Go to distribution menu, just like inverse norm. It might not be there. Depends. Some have it, some don't.
Oh, yeah.
I don't have it. Do you have it?
Yeah.
Give it a shot. Tell us what you get. And when I can't put it on the big screen because you know what? My calculator doesn't have it. That's okay. We use the table. And when I'm like you with the 83, it's old school. It's no problem. I can read a table. I'm not going to go buy a whole new calculator just for this one what? Inverse T. You could probably download it off the internet if you want. But I'm like, oh, this will work. This will work. Who's stuck like me with the table? Oh, good. Now, if you want to use calculator and get that inverse T, you can. Just don't forget, hey, you got to put the comma degrees of freedom.
Yeah.
Because it changes depending on the sample size, right? Good job. You have it?
How did you get 1.664 then?
Okay, so when we looked at that sheet, we looked in the left column for degrees of freedom. We saw the closest number to 71, which was 80. Then we went over to the right and we looked at the bottom of the sheet where it said 90%. At the bottom of the sheet, we lined up 80 with the 90% and we got the t-score of 1.664. I do want to point out, if you look, Preston, at the top column, then you're going to have to look at a 0.05 because that's what's in one table. So that's why it's easier to look at the what? Look at that bottom, because it just tells you.
The calculator gives you something different. Well, not a lot, but it's like.
Oh, she's right.
1.6.
The calculator's more accurate. Tell me what the calculator said.
So, like, for example, since I take the test on, the computer.
Oh, you're going to be fine.
that-
Because think about it, you got a lot of students like you who are using TID3s. So that's going to be fine with this number. But hey, tell the class, what number did you get when you put this in there?
Negative.
First one's going to be negative because it's going to be on the left. But negative and positive, it's symmetry, they're going to be the same. And what did it come out to be?
Negative 1.6665.
So look, it was very accurate to at least 2 decimal places, which is fine. But you're going to be fine because they know that. The programmers of that know that probably at least 50% of the students, if not more, are using TI-83 calculators. So you're good to go. Good question though. Plus, a lot of times, you're going to notice in the MyStatLab, they provide a table. You only even have to have this next to you. The way I click on the distribution table, and you can get it off the table.
Do they have
It's a
this
great
on,
question.
on TI-92?
TI-82 has it, yep.
They have it.
Yeah, all the new ones.
I'll look.
It's just the old 84s and the old 83s.
Sure.
Well, 83 being old, yeah. But I have an 84, everyone. You see it up there. Mine doesn't have it. I'm curious, who had it? Denora, you have it? Randy has it? Look, it's only it's less than 10 students. So can you imagine this? I have some colleagues who think every student should have to have these new calculators. That's a lot of money, isn't it? You think it's worth it? You go spend $140 just because
Just for
you
one
don't?
function.
I think this is a little bit cheaper. Do you agree?
Yeah.
I mean,
Yeah.
I'm with you. I'm with you. All right, I'm gonna erase all this, everyone. Let's find this number. So get out your calculator. I want you to find this number after the plus minus. And you and I will be done with the confidence interval. 242.2 plus or minus. What's this number though? And we'll got to like 1 decimal place. What do you get when you go 1.664 times that? I'll do it too. Only takes a second. I just want to get that. By the way, do you remember what we referred to after the plus minus? What's the name of this? Everything after the plus minus?
Margin of error.
Margin of error! Thanks, Art. Cool. All right, here we go. And I just want to see what the margin of error is. What's 1.664? Denora gets to write hers more accurately with the 1.666. I know. 1.664 times 70.6 divided by square root. Whoops. Square root of 72. You don't even have to close out the parentheses right there, but I'll do it. Looks pretty. All right, what's the margin of error?
13.8.
And they're really newtons, so you can go 13.84 newtons. 13.8 or 13.84 newtons. I'll hit the lights. And when there it is. This is the what? Confidence interval. And yep, everything after the plus minus is the margin of error. Do you remember I encouraged this last class? I encourage everyone to write the confidence interval in 2 ways. So I'm going to do it now. This is one way. This is full credit. That's your confidence interval. But I'm going to put or. I encourage you to write it like this, as an interval. And it's very simple. All I have to do is take this number and subtract that, and take this number and add that. I'm going to do it with my calculator, okay? So I'm going to hit the lights. I just want to see what these 2 numbers are. All right, what is?
And it's from lowest to highest?
That's right, you always go lowest to highest. Always go from lowest to highest. So what's 242.2 subtract 13.844962221? And what is 242.2 plus 13.8449622? What are my 2 numbers? 228 point what? 35, 228 point, all right, now around this, what is that?
36.
36, and what's the other number?
256.05.
That'll work. And feel free to round that to 0.4, these are final answers. So you can round them. That's it. I encourage you to write it both ways. What were the units on these? Do you want to put the units?
Newton.
These were newtons. You want to put newtons in here. This is newtons. You can put newtons and newtons. And we're going to interpret this. This was the force. We're talking about with that resin cement, right? They called it the strength, tensile strength. But it really is the tensile strength of this, of that cement they got in there. How strong is it? Is it going to hold that teeth in, that crown in the mouth?
Yeah. 256 for like the.
Oh, thank you so much. You bet. Thank you so much. There's a 256 point there. Awesome. Everyone good with this? So now, that's A, that's B. I'm going to erase this. Letter C. Everyone can interpret this in your own words. I'll leave this up here, by the way. Can you interpret this in your own words?
So with 90% confidence.
Oh, I'm going to write that. With 90% confidence,
Inter.
with 90% confidence, I'll put a comma.
Uh-huh.
The
Mean.
good. Is it a sample mean or population?
Population mean.
The population mean, if you want to write after this word mean, everyone, if you want to put tensile strength of the teeth, of the crowns and all that stuff, it's actually cement. But the population mean is between what two numbers?
228.36, comma 256.
And 256.05 newtons. Are we 100% confident? No, but we're 90% confident. And I always like to repeat what this means. I am 90% confident. This means, everyone, if I did 100 more sample sizes, like 72 teeth, with a bunch of dentists, over and over and over again, what I'm saying is 90 out of 100 of those experiments, all right, would come up with X bars that are between these two numbers. That's what we're saying. That's what we're saying. 90 out of 100 would capture a number like this, they'd be inside here. All right? That's what we mean. So we're saying we're 90% confident that the population mean for that resin cement is between those. Cool? But that's what it means, right? What do you mean by 90% confident? It means if we did 100 more of these, get 72 teeth, get 72 teeth, get 72, keep doing this, 90 out of 100 of those confidence intervals, all right, would actually capture this, this true population mean we're looking for, and they'd all have this number, that their X bar would be somewhere inside there. Does that make sense?
Is this T distribution available in Google?
Yeah,
It's
yeah, it does.
It does.
Awesome. Hey, I'm gonna erase this, letter D. What's the margin of error? What's the margin of error?
256 minus that.
Margin of error is right there, right? Oh, after the plus minus, which is plus or minus 13.84 newtons. Letter E, when you okay if I just read this to you, you're going to answer? Let me know if you need to repeat this. This is going to be the same letter E's from last class. And here it goes. If these researchers did this experiment again, and they wanted to decrease the margin of error, what should they do?
Increase them.
Yep. I'll repeat it. If the researchers wanted to do this experiment again, with the teeth and the crowns and all that, but their goal was to decrease the margin of error. To decrease the margin of error, what should they do? And the answer? They should increase the sample size. Good job. Increase the sample size. Increase N. Jack up N. Get more teeth. You need more than 72 teeth. That's what you need. Don't I get that? Autumn will be happy we're not doing an F on this, dude. She's like, oh, cool. We're not doing an F on this. before we move on to the next problem, you know exactly what we gotta do. Come on, that was a lot of math in there, right? You saw the math I was doing with the tables and stuff? Isn't there probably a faster way? And what's great is, all 83s and all 84s have this. So you know where this is where you're gonna find out, like, oh, now we're good. Oh, now we're all good. Cool? So we're gonna go back, I'm gonna go back to this board, and I'm gonna pretend like I'm gonna use the fast way to get all these answers. Sound good? You know, I wanna motor through this like within 1 minute. A lot of students like this. That means I'm not gonna do any of that what? Multiplication of this times the standard deviation, all that stuff, right? True? I'm like, technology, facilitate this for me. I'll still do my interpretation, so I'll leave this up here. But everyone, I'm gonna pretend like I don't have B, or D, or E. Sound good? Can I erase? Alright, so everyone look. I don't know what B is. There's C. I don't know what this is. I don't know what this is. And I don't know what this is. D asked for the margin of error. B asked for what's the confidence interval. And E asked, what should you do if you need to decrease the margin of error? Well, we already know that answer. What's that going to be?
Increase them.
Yeah, we're going to increase the sample size. I'll just put that down. Alright, so which two are we looking for really?
B and D.
Alright, let's go over here. We'll go to the calculator. This is a rock and roll button here. We love this thing. It's in the stat menu. It's in the test. Alright, so I'm going to hit the lights. Oh gosh, please use this. All 83 and 84 calculators have this. Stat, test. What are we looking for? Interval, right? Last class, 9.1, we did something called a 1 prop z interval. So Denora, I do want to point that out. We did a 1 prop z interval for 9.1. It stood for 1 proportion 0. Now we're looking for something called a t interval. Because you know we're using what? T. Where is t interval? I still don't see it right there.
Number 5, 1 prop Z. No,
So I'm looking for a t interval. It's not even up there right now. So I gotta scroll and scroll and scroll and... Yay! There it is. It's number 8. Someone see it? Now, I think this is self-explanatory. Watch. When I hit the screen, you can be like, look at all the numbers we wrote down. Tell me what to do. Everyone, I'm hitting number 8. I highly recommend this. Now you got data and stats. Data would be like you went out tomorrow, collected data, did stuff yourself, and did your own project. Well, we're just getting the statistics off this textbook from the calculator. So we're going to use stats, highlight that. What's export? 242.8. What's SX?
Same.
70.6. Someone agree? Sample standard deviation. What's N? What's lowercase n?
72.
72. Everyone knows what to do. What about here? What do I do here? A lot of times this is 0.95, but on this particular problem it was what?
0.90.
It was 0.90. What do y'all think? Now this should give us the answer, right? What's the confidence interval?
14.
There it is. I'm going to hit it up here. That was pretty easy, right? What's the confidence interval? 228.33. What's the other number? Now, is this a little off from what we had before? Yeah, because I used a t-score off what? This sheet, Denora. This is even more accurate, right? But both answers are totally fine because some use the sheet. I have to make sure I'm okay with both of these. Because it is estimates, and that's what we do in stats. All right, now I'm stuck though. Sad face. So when I'm going to hit this, turn this off, let's say I'm on a test. I used the shortcut me. I like that button. That was it. I didn't have to do any math. Thank you for giving me comments and I go and I interpret it. With 90% confidence, the population mean is between these two numbers right here. Oh, and I'll adjust for the new calculations I just got. It's a 0.07. All right. Woo, okay. I'm stuck now. How do I get the margin of error? All right.
Subtract the lower from the upper and divide by 2.
That'll work. And when he goes, this is Art's way, it works every time. He goes, take this, subtract this, and divide by 2. You can do that. Here's another way. I'm going to draw a picture. You know how I like pictures. That's the low end, right? What's the high end? What's the highest end?
256.07.
Who's smack dab in the middle?
Mean 242.
So you can use Art's method. You may prefer to use, you take this, you subtract this, you divide by 2. Or if you want, you could just take the high end and subtract the what?
Lower.
Because that's a margin of error. Your margin of error is from the middle out.
You can go here to here, or this minus this, and you will find your what? Margin of error. So Denora, everyone, no more set base. That's all I gotta do is just take that, subtract that, or do what Art said, this minus this, but then you'd have to divide by 2, right? Here's the biggest error. I get students who only subtract these. They doubled it. They just doubled the margin of error. The margin of error is only a portion on one side, right? The margin of error is from here to here. So what I'm going to do, I'm going to just take this number, I'm going to subtract that number, and I'll get my margin of error. What is 256.07 minus 242.2? 13.8487, is that what it is?
8, 7.
Ah, it was even more errors, but an 8.7, you want to make the 0.9. Everyone okay with this? Awesome. Hey, the remainder of class, I'm just going to talk about 10.1, which is an intro to hypothesis testing. Can I raise? Hey, summary for your notes. What are the cool buttons from that test menu? For 9.1, who is the cool button? Letter what? Letter A? And what was the cool button for 9.2? Number what? Number 8. Everyone got that? I'll put quotations around it. Those are the rock and roll buttons from that menu. Now for the remainder class, this will be fun. I am going to introduce you. We're not going to perform a hypothesis. I'm just going to introduce you to it, okay? So we're going to do a setup of a hypothesis test. This is called Introduction to a Hypothesis Test. Just put intro to hypothesis test. Now this course gets a lot of fun. Because I want you to leave this course and go perform your own hypothesis test. Hypothesis test, a hypothesis is an educated guess. Do you know that? That's what it is. A hypothesis is just an educated guess. But in this course, you learn the statistics. We can use the statistics, all right? And we can see if something's maybe statistically significant or not. The results we get. Which could say, hey, I was kind of right with my gut feeling. So I'm going to give you an example. All right. When we set up a hypothesis test, there's 2 things we put. We put something with an H sub 0 and we put something with an H sub 1. This is called the null hypothesis. That's called the null hypothesis. That's called the status quo. You go, what do you mean by the status quo? That's what's going out there. That's what we know about in the world. That's what everyone tells me. That's what my mom told me. That's what my job told me. That's what my government told me. That's what my company tells me. That's the actual population mean, or that's the actual population proportion. That's the status quo. This, though, is going to be the alternative hypothesis. All right. That's your educated guess. That is your educated guess. So I'm going to give you an example. Here's the story. All right. Everyone, let's say I've been a nurse for 25 years, right? Every daggone day, except when I'm off work. You know what I'm doing? I mean, I'm doing a lot of things in my job, but one thing I'm doing, I'm taking body temperatures. People come in ill and all this. I've got sick babies, etc., but I'm always taking a body temperature. Now, who in this room knows what's going out there in the world, what we've been told by parents, relatives, friends? What is the status quo for the mean body temperature?
98 something.
98.6, that's what I was told. All right, now that would be given to you in a problem. They would state that in the first sentence. They always state the status quo in the first sentence. So the first sentence would read this, Autumn, all right? It's well known that the mean body temperature of human beings is reported as 98.6 degrees Fahrenheit. So up here, everyone, the word mean came up. Now we're talking about a population. So I'm going to use this mu symbol, because that's a mean for a population. I'm going to put an equal, and I'm going to put 98.6 degrees Fahrenheit. So I'm setting up a hypothesis test. That's what I'm doing. So what we're doing right now, everyone, you and I are setting up just the initial part of a hypothesis test. The author felt it was important that they just take one section of the book to make sure students know how to set this up. So what goes in here, I've got an H sub 0, and that's called, you can say H sub 0. Some statisticians and scientists like to say H naught. Have you ever heard that before? H naught. So if you took a physics class, They go the initial velocity, and they go, that's V naught. They go V naught, they just use the word naught for that. So you can call that H naught or H sub zero. Yes, some students call it ho. I don't care if it's okay if you call it ho, I know. Ho, alright, that's the ho. But the mu is equal to 98.6, that's the status quo, right? And when every time, you're gonna use the same symbol right here. So if I put a mu here, what goes here?
Mu.
You gotta use the same, you know, they call it a parameter. This has to be the same number here. Alright, so I'm gonna leave a box here right now. Really like, what goes here? What symbol goes there? It's one of three things. It could be a greater than symbol. It might be a
Less than
less than symbol,
or equals to.
you know? And if you want to put equal signs with the, it doesn't matter. Or the last one, they might put a not equal to symbol. Alright? And you go, which one are they going to put? It depends. It depends on the researcher. So can I finish my story about the nurse? You're going to tell me what to put there, alright? So the first sentence, Autumn, I'll repeat it. It is well known that the population mean body temperature for human beings is 98.6 degrees Fahrenheit. Okay? A nurse over at Anne Arundel Medical Center believes that it's less than that. Which symbol do you think I'd use?
All the way.
Alternative hypothesis. I'll repeat the second sentence. A nurse working at the Anne Arundel Medical Center who's performing this research believes it's less than that number. Which symbol is less than?
All the way
Oh,
to the
some
right.
people don't know their math symbols. Which one's less
All
than?
the way to
Is
the
that
right.
one right? That one great? I saw some faces. No, you got it. Well, I'm gonna use this one, right? For less than. True? Think of it like an arrow. Lower. Just think like lower, right? That symbol. This would have been if it said what? Greater than.
Greater than.
Would you put this in your notes? When do you put the not equals to? If they say is different, if they use that wording, or sometimes there's another phrase they like to use, if they say has changed. So when if they say is different, or if they say has changed, they haven't indicated if you're going greater than or less than. I'm going to put a not equal to. Okay? Now next class, when you and I are going to perform a hypothesis test, and when it's this, they call this a right-tailed test, and you and I will shade the right side, it'll be fun. When it's like this, you and I will perform bell curve, but we're going to shade the
Left.
left side. You know what you do when it's a not equal to?
Center.
They call that a two-tailed test, and you have to shade both tails. Don't worry, I'll talk about that next class. Cool? So if you want to draw these now, you can, but that's coming up in 10.2. Right now, we're only in 10.1. So I'm going to read something from the book, and I'm going to have you set it up for me. Does that sound good? Yeah? All right. Let's see how good you are. Ready? Can I raise? Remember, what symbol's always here?
The mean.
No matter what, equals here. This can be a mu, or it could be, what's the symbol for population proportion? That symbol. When do you know you got to use the row symbol? And when that's row, if they give you percentages, okay? So you got to determine which symbol to use. This is always an equal sign. This can be one of three symbols, right? All right, let me try one. Can I raise? All right. Let's see how good you are. Everyone, you can lean that up because that's always there. This is always here. This is the null hypothesis. This will be the alternative hypothesis. By the way, I do want to point out, a lot of you might read literature on the internet. You know, you like to research statistics on your own. Some stat books use an A here for the word what? Alternative. If you prefer that, please feel free to do that. Some stat books put H sub A for alternative hypothesis. But your textbook uses this. I want to stay consistent. I'm going to put an H sub 1. All right. And when I am on page, let's see if you can crush this. You got to set up this hypothesis test. Hey, Autumn, I'm going to pick one of the three problems from this section. So you'll be able to do it again. But let's see if you can get this. I'm going to pick number 15. It's on page 483. All right. What is on page 483? Number 15. And this is in section 10.1. All right? You go, what do you got to do? You just have to set up the hypothesis test. The author knows if we don't set this up right, the whole problem's going to be over. All right, the first sentence. It's titled Teenage Mothers. according to the US Census Bureau, 10.5% of registered births in the US in 2007 were to teenage mothers. Okay? Now that's the first sentence. So guess what that is? The what? That's the status quo, right? That's where they're getting this number. It's like some number they got from Census Bureau, right? That's our government. They figured this out. So our status quo is you're getting 10.7%. I'm going to put it over here. Am I going to use this symbol or am I going to use that symbol?
Row.
I'm using rho because it's a percentage. Anyone hear that? It's a proportion. So I'm going to write rho, not you, equals, and what was it? 10.5%. Now, do you want to write it in this format or do you want to write it as a decimal? I'll write it like that. By the way, what is that decimal in case someone here wants to write it as a decimal? That's 0.101.
5.
In case you want to write it. Hey, almost done with this problem. This has to be the same parameter. That's the row. What's this?
Mu. Is a row.
It's the same symbol. It's got to be the same one. This number here, everyone, it's got to be the same number. So far, so good? But Autumn, this next one depends on the wording they use in this next sentence. So everyone listen to this. The next sentence. A sociologist believes that this percentage has increased since then. What am I writing?
So greater than.
You know, if that helps, think arrow. Increased. You know, the arrow helps with the symbol. There you go. And next class, we'll perform like a bell-shaped curve, and we'll shade on the, we'll do a right-tail test. Hey, one last thing we gotta talk about. There are two types of major errors that occur in stats. Okay? One of them is called a type 1 error. And one of them is called a type 2 error. So when you write your report, you might mention these. I'm serious. You might say, to decrease the likelihood of having a type 1 error or type 2 error. I want to explain what happens here. A type 1 error is when the null hypothesis is true, and the researcher, sociologist, nurse, etc., mistakenly rejects the null hypothesis. I'll put it here. Let me repeat this because I know a lot of you are copying this. What's a type 1 error? It's when I put the H not, the H sub 0, the ho. It's when the ho is true, type 1 error, all right, when the ho is true, when the null hypothesis is true, but the researcher does a hypothesis test and mistakenly rejects the null hypothesis, the ho, yeah. So that's the type 1 error. It happens. By the way, you remember Gossett? Gossett kept making type 1 errors. He knew there was trouble. Gossett kept making type 1 errors. This is the opposite. This is when the H1 is true, which is the alternative hypothesis, and the researcher, I'm going to put a word, everyone, and then I'm going to change it, okay? The researcher retains, all right? Retains. The H1 is true, and the researcher, remember, he makes a mistake, so I'm going to write mistakenly. H1 is true, and the researcher mistakenly retains
Oh.
the ho. H sub 0, the H not. But everyone, I'm going to cross out this word retains, and I'm going to tell you how statisticians talk. You go, can I use that word? You can't use the word keeps. You can't use, retains is probably the closest verb you can use, but we just say, in place of this, to not reject, we just say does not reject, or fails to reject. And I'll explain why. A lot of you are sitting there going, why can't you just say retains? Like keeps it. This is like the courtroom, everyone, with law. Is anybody going into law? Everyone, you know this. At the end of the trial, do they go up and go, do you find the defendant innocent or guilty? Is that what they say? Thank you. You've seen enough TV and stuff. That's not what they said.
Guilty.
Do you find the defendant innocent or guilty? That's not what they said.
Guilty.
What do they say?
Not guilty.
Do you find them guilty or what?
Not guilty.
Not guilty. Do you follow me? There's a reason for that, because everyone's assumed to be what?
innocent.
Not guilty, right? We always think this person's not guilty, we see if we have evidence against them. So in this case, it's just like the law. It's just like in the courtroom. We can either reject HO or we just say keep it. We don't know if it's true or not. We're just saying perhaps someone didn't have evidence to go against it, so we fail to reject it or do not reject it. So in this case, if on the test, if I said, hey, I need you to set up hypothesis tests, and then letter B, I say, I need you to explain what a type 1 error is, what would you say? What would you tell me? To explain what a type 1 error means, what would it be?
How is true?
Yeah, null hypothesis is true. And then what was the mistake the researcher made? The researcher mistakenly what? Rejected it. Now, you might say, hey, before you leave, I'm going to confuse us on a test. I'll tell you what I do. You may think this is stupid, I don't care. This is what I do. I think of the word hop for this one. So I think, oh, ho is what? T for true, and then I think the researcher made a mistake. So what happened? If the ho is true, he made a mistake, he or she made a mistake, what did they do? They just rejected the what?
Okay.
Rejected it. Does that make sense? So I just use that as a way to help remember it. I think a hi. This you can do hit. Right? Hey everyone. Great job today. Have a great one.